Hello gents, welcome back to another video. In this video, we'll be discussing all the derivations from the chapter electric charges and fields. Now in the previous video, we discussed all the concepts in that chapter. So if you wish to watch it, I'll make the video available in the description box of this video. Okay, this video is especially important for boards. In the previous video, we could not discuss how the relations were being derived. So this is a video justifying that. Okay, so here we'll be doing all the derivations. If you want to learn the concept, that is the video you should watch. Okay, so let's begin with this one. 10 to 12 derivations in this chapter, and we'll be discussing them one by one. So the first one is the Coulomb's law. We'll be discussing it in scalar form and vector form, and also show that in the vector form the Coulomb's law is in accordance with Newton's third law. Okay, so the scalar form is easy to derive. It's directly derived through the statement. What does the statement of Coulomb law says? It says that the electrostatic force between the two charges Q1, Q2 point charges, these are separated by a distance, let us say r, suppose. Okay, this electrostatic force is directly proportional to the product of these charges, okay, and divided by the square of the distance between them. Right now, mind you, this is only the magnitude. We are writing in the scalar form as of now. Okay, so this force will be the magnitude, we can say k q1 q2 by r square. Okay, this k is some constant of proportionality. Okay, and this k is experimentally found to be 1 upon 4 pi epsilon naught. Okay, this epsilon naught is the permittivity of free space. This k itself has a value of 9 into 10 to the power 9. Okay, and if you see the units of this k, it will be Newton. Meter square per Coulomb square, right? Newton meter square per Coulomb square. Okay, and if you want the value of this epsilon naught, this actually depends on the medium. It will change if you place these two charges in some other medium. This, as of now, we are considering they are in vacuum. Okay, so this epsilon naught in vacuum has a value of 8.85 into 10 to the power minus 12. Okay, and the units will be just opposite of that because it's inversely proportional to C. You can see Coulomb square by Newton meter square. Okay, Coulomb square by Newton meter square. So if you plug in this value over here, you will get the value of k. Now that is about the scalar form of our Coulomb's law. Let us derive the Coulomb's law in vector form and show that it is in accordance with Newton's third law, that the two forces on one charge due to the other and on the other charge due to the first one are equal and opposite. Okay, so for that we'll write it everything in vector form. So here we have q1, q2. We'll choose some origin. Okay, origin is over here, O. Okay, so we'll connect this point q1 with the origin. So this is our position vector r1. Okay, we'll connect this O to q2. This is our position vector r2. Okay, now this position vector, you can find it by triangle law. This plus this should be r2, right? This plus this should be r2. So this will be r2 minus r1. Okay, so if you add this two, you'll get r2. R1 cancels and you'll get r2. Okay, that is simply done by using triangle's law, okay, of vector addition. So this can be also r2 minus r1 is also denoted as r21. Okay, rab is ra minus rb. Okay, so r2 minus r1 is r21. Okay, now let us write a Coulomb's law. So we'll write F12 and F21. Okay, so F12, what does that mean? That means force on the first particle due to the second one. Force on the first particle due to the second one. Okay, so F12 will be K, which is 1 upon 4 pi epsilon naught q1 q2, again in accordance with your, now this is a vector. Okay, we'll use we are writing it in vector form now. So q1 q2, product of the charges and the distance between them. Now this force is the force on first one due to the second one. Now let us assume that both are positive, both are like charges. So this force will be along this direction, right? They will be repelling each other. So this q2 will be exerting a force like this on q1. Okay, they will be repelling each other. Okay, so for now, what is the distance between them? R2 minus r1. Okay, I'm taking the magnitude because it is the distance, right? So r2 minus r1, that position vector, the magnitude of that position vector will give us the distance between them. Okay, Now we also have to specify the direction. This is just a scalar now. We also have to specify the direction. We can see that the direction is opposite to r2 minus r1, right? r2 minus r1 is in this direction, whereas this vector, the force on the first particle due to the second one, is along this direction. r2 minus r1 is along this force is along this, okay? So it is opposite to, we can say minus r21, or we can say r12, right? That will be simpler to remember. We'll use a unit vector, okay, to denote the direction so that it does not affect the magnitude, okay? So it is along this direction, r12, okay, opposite to r21. r12 will be r1 minus r2, okay, so the negative sign, okay? Or you can also write this as 1 upon 4 pi epsilon naught q1 q2 r2 minus r1, okay, this whole square, okay? And the position vector r12, the unit vector, if you know, it can be expressed as your vector divided by its magnitude, okay? You might see this definition being used in your NCERT. So this can be written as r1 minus r2 upon magnitude of r1 minus r2, okay? So if we write this r12 in this form, we'll get r1 minus r2 over here, okay, and we'll get the magnitude of that, right, in the denominator, and this is also the same term, r1 minus r2 or r2 minus r1, the magnitude of that is the same. So we can basically say this is the whole cube, okay? So it might be also written in this form, in vector form. You might see this being used in your NCERT in vector form, okay? Don't need to confuse this cube, okay? It comes from the unit vector, okay? So similarly, we can derive the force on the second charge due to the first one. Now I said both of them are like charges, so they will repel each other, so force is in that direction. So again, 1 upon 4 pi epsilon naught, now we can directly write this, we'll have q1 q2, again product of charges, the distance between them r2 minus r1 magnitude, okay? Now magnitude square of the distance, right? And we have to specify the direction. Now you can see that the force on the second one due to the first one, 2 due to 1, okay, this is along the position vector r2 minus r1. r2 minus r1 is along that direction, and the force is also along that direction, okay? So you can write r21 position vector, okay? Or you can write it in this form, where I can say it is r2 minus r1, okay, the vector divided by its magnitude. This is the magnitude of, so it will say r2 minus r1, right? This and this will club together to give you a cube, okay? This cube comes only due to the position unit vector, okay, this unit vector, okay? Now you can easily see that this force F12 is minus of F21, right? Because this is r1 minus r2, this part is same. You can see that 1 upon 4 pi epsilon naught q1 q2 r2 minus r1, the whole cube. This part is the same. Here is the difference, r1 minus r2, r2 minus r1. So these two forces are equal but opposite, equal in magnitude, opposite in direction. So Coulomb's law is in accordance with your Newton's third law, okay? So this is the proof for it. Let's move to the next derivation. Discuss derivation number 2, which is electric field due to a point charge. So we'll choose our point charge as capital Q. This is the source charge, okay? Source charge meaning the charge which is producing the field, okay? We'll have to use one more charge which we'll call small q naught, okay? It is the test charge. It is used to test the charge due to the source charge Q, okay? These charges are at a distance, let us suppose r, okay? So if they are like charges, this charge, source charge Q, will repel this one with a force F, right? Now the definition of electric field, it says that limit Q naught tending to 0, okay, F by Q naught, okay? This is how the electric field is defined. Now this Q naught has to be very small. Why? Because it should not influence the field of your source charge Q, okay? That is the reason why this Q naught should tend to 0. It is only used to test the field due to the capital Q, okay? It will not appear in the relation of electric field due to the source charge Q, okay? You can see that. So we'll derive it. So limit Q naught tending to 0, 1 upon Q naught. Now force, we can write it in the form of Coulomb's law. These are 2-point charges, so the force will be given as 1 upon 4 pi epsilon naught q naught by r square. Okay, so now we can cancel this q naught. As I told you, it will not appear in the electric field relation, so electric field will be simply 1 upon 4 pi epsilon naught q by r square. Okay, there is no q naught term, so no limit for that. Okay, so this is the relation that we obtain. Now electric field is also a vector. You'll understand this better if you have seen the last chapter and the nature of electric field lines. Okay, so basically this electric field will be have the direction same as that of force. Okay, or it may be anti-parallel, but in this case it will be along the same direction because we have chosen the capital Q as positive, right? So if we say that this r vector is along this direction from capital Q to radially outward, so this electric field will be along the same direction outward, okay, with positive charge, and inward if it was minus r cap if it was negative. Okay, so that's about electric field. Let's move to the next derivation. To derivation number 3. Here we'll be discussing the electric field due to a dipole at an axial point. Okay, so what is a dipole? These are basically two charges equal in magnitude, opposite in signs, plus q minus q, plus q minus q, separated by some distance. Okay, let us call this distance as 2a. Okay, they are separated by a distance 2a. So we have the center of dipole, and we can define this distance as a and this distance as a. Okay, now we have to find the electric field at an axial point. Okay, so let us do that. So where is the axial point over here? The axial point will lie on the axis of the dipole, right? So this is the axis of the dipole. So let us choose the point P somewhere over here. Okay, this is on the axial point. Now we have to find the electric field at that point. Now let us define this distance from the center of the dipole to the point P as the distance r. Okay, this r will appear in the electric field relation, this relation. Okay, and you have to remember that the r is always measured from the center of the dipole. Distances are always measured from the center of the dipole. Okay, please remember that. That is an important point. Now you can see that the point P from plus Q is at a distance of r minus a, right? So this is r minus a, and you can see that the point P from minus Q is at a distance of r plus a, right? So this is r plus a, right, from point P to minus Q. Okay, so that will be important. Now let us find the net field. The net field can be basically given by a superposition theorem, that the field will be basically the sum of the individual fields produced by the individual charges, right? So the vector sum. Okay, that is very important. That is your superposition theorem. So it's actually we can use it very simply, because here if you see this is positive charge, so it will be the field due to that charge will be E1 in the outward direction. Okay, and let us suppose that the field due to this minus Q is E2. Okay, it will be slightly less because it is at a greater distance, right? Plus Q is closer to point P, minus Q is away from point P. So E2 is like this. Okay, it is lesser in magnitude. Okay, this electric field due to point charge is inversely proportional to the square of the distance, right? So it is slightly lesser than E1. Okay, and the net field you can see E1 minus E2. These two fields are in the opposite direction. Okay, so you can basically take the magnitude of this field, and subtract the two. Okay, we'll be only considering magnitude and subtract the two. Okay, we don't have to look into the angle between them. The angle is basically 180 degrees, and it is simplifying the case. Okay, so E1 will be excuse me, sorry, E1 will be this 1 upon 4 pi epsilon naught. If you see, E1 is due to this point charge, so it is at a distance of r minus a the whole square, and E2 will be 1 upon 4 pi epsilon naught q. Okay, now I am not taking minus q because we are only considering the magnitude. We will be subtracting them at the end of the day. We know that the two electric fields due to plus q and minus q are in the opposite direction. Okay, so I am only considering the magnitude and subtracting the two. Okay, so basically mod, and here the distance is r plus a. So E net will be or E axial at that point P will be E1 minus E2, right? So we can take common for Q upon 4 pi epsilon naught, and here we will be left with R minus A square and minus R plus A square, right? This is minus, and let us solve it further. We'll get same thing outside the bracket, and here we'll get this will be R minus A, R plus A. So I'm just crisscrossing now, and I can write this as whole square. Okay, R minus A, R plus A, and both are squared. So R plus A the whole square minus R minus A the whole square. So R plus A the whole square minus R minus A the whole square. Okay, let us simplify that further now. So here we get, so this is R plus A, R minus A. Okay, so that will be R square minus A square, right? And this is the whole square. Now if you see, only 4AR will remain over here. I'll simplify it and show you. R square plus AR plus 2AR, and here we'll get minus R square minus 2AR plus A square, right? So this R square and this R square will get cancelled, A square and A square will get cancelled. This will become plus. So we'll have Q upon 4 pi epsilon naught 4AR divided by R square minus A square the whole square. Okay. Now you know that the dipole moment, we discussed it in previous class, it is Q into D, right? Charge into distance of separation, either of the charge into distance of separation. Okay, now we are just considering the magnitude. I'll comment on the direction towards the end of the derivation. So let us isolate 2R from here. Q into 2A, that will give us P, and we'll be left with 2R, right? We remove 2A from here, we are left with 2, one of the 2's is gone, and R is also there. Okay, and here we have 4 pi epsilon naught R square minus A square the whole square. Okay, you can remember this is the electric field at a axial point. I can also write it as 2 kpr, this is k, right? 1 upon 4 pi epsilon naught R square minus A square the whole square. Now usually the dipole, the distances between the dipole is very small. Okay, A is very small as compared to R. Okay, so we can neglect this A. So suppose how you can neglect, because R square is very big, right? So suppose if you remove 1 from 1 lakh 1, okay, 1 lakh minus 1 is still about 1 lakh, right? So we can neglect this A when it is very small. Then the distance R, okay, of the axial point. So here we'll get 2 kpr upon R to the power 4, or you can write the field at the axial point is 2 kp, R and R will get cancelled, upon R cube. Very important to note that the electric field due to a dipole is inversely proportional to R cube. Okay, in case of your point charges, it was inversely proportional to R square, right? Now let us comment about the direction. You can see that the dipole moment due to this dipole is from minus q to plus q, right? It is in this direction, and the net field will be also in the same direction, right? E1 minus E2. E1 is greater, so it will be, the net field is in that direction. Dipole moment is from negative of the charge to the positive. I told you this in the previous class, right? So the electric field at the axial point is same as the dipole moment, okay, the direction basically. Okay, and remember that relation. Okay, when we derive for the equatorial point, it will be very close to this only. Okay, it will be inversely proportional to R cube, but it will be half of this. Okay, we'll derive that in a while, and something with the direction. Okay, we'll derive that next. Okay, so here at the axial point, the direction of the electric field and that of the dipole moment are in the same direction. Okay, so if you had to flip the dipole, you can see that if we had minus q over here plus q over here, the dipole moment will be this way, and the electric field due to the negative charge will be more now. So this will be more. Okay, so again electric field and the dipole moment are in the same direction. Okay, at the axial point, of course. So let's move to the next derivation now. And electric field due to a dipole at axial point, at equatorial point. So here we have the dipole plus q minus q, again separated by a distance 2a. Okay, now at equatorial point, meaning a point on the perpendicular bisector of this dipole. Okay, so these two sides are equal, so basically this is passing through the center of the dipole, okay. And you can also prove that these two are similar triangles. It's not looking like that, okay. So these two triangles will be similar, so if this is theta, this will also be theta, okay. Now we have to find the electric field at point P over here, okay. It's actually simple. We'll do the same thing that we did previously. We'll find the two electric fields individually and add them vectorially, okay. So here if you see, due to minus q, the electric field will be in this direction, pulling towards the point q, right, radially inward, and due to plus q, it will be in the outward direction, okay. So these are the two fields, E1, E2, okay. Now you can also see that now E1 and E2 are such, right. So E1 is like this, E2 is like this. You can see that the angle that align parallel to this will form theta with this, right, because these two are corresponding angles. This is theta and this should also be theta. These are two parallel lines, this is a transversal, this is corresponding angles, and if you see this and these are alternate angles, so this will also be theta, okay. So the angle between these lines are theta, okay. So you can see that now these two charges are equal, so I don't have to write E1 and E2, okay. Same distance over here, this distance d, let me call this d, okay. So the distance d is same, and I'll call this perpendicular distance y, okay, basically because it is along the y axis, okay. So this E will be equal, okay, they will be equal in magnitude because the charges are same, right. Now we'll consider the directions, and you can see that we can resolve this E into two components. So the first one, if we say, it will be E cos theta along the axis, right, and E sin theta perpendicular to the axis, okay. Along the axis E cos theta, perpendicular to the axis E sin theta, okay. This is something which we learn in the resolving of vectors. Here also, perpendicular to the axis E sin theta and along the axis E cos theta, okay. So basically the sine components will cancel out each other, okay. E sin theta and E sin theta will cancel out each other, okay. Only the cos components will survive and they will add up, right, they are in the same direction. So your net field will be 2E cos theta, okay. E cos theta due to this and E cos theta of this, okay, due to minus q and plus q, so 2E cos theta, okay. Now let us substitute this. Now we'll define this distances. This is the center of the dipole, so this distance is a, this is also a. Now using Pythagoras, now this is perpendicular bisector, I told you, right. So using Pythagoras, you can define d as the square root of a square plus y square, right, it is the hypotenuse, okay. Now let us find this electric field at equatorial point P, okay. So this is 2 into, now you can take field due to any point minus q or plus q, okay. We'll take plus q, so 1 upon 4 pi epsilon naught q by r square. So it's basically one component. R square is the distance between the charge and the point P, so you can see that the distance is d and it will be squared over here, okay. So d square will be, basically you can write it this way only, d square is a square plus y square, and we also have cos theta, okay. Cos theta we can also find from this triangle. So you have 2 into 4 pi epsilon naught q, d square is, you can write a square plus y square, a square plus y square. And what is cos theta? Cos theta is adjacent upon hypotenuse. So adjacent, which is a upon hypotenuse, which is d, d is square root of a square plus y square. So a square y square raised to half, right? Square root means raised to half. Now you can easily see that this is q into 2a, right? Q into 2a. So that is dipole moment P. As of now, we are not not concerned about the direction. And this is y square plus a square, y square plus a square. This is half plus 1, this is raised to 1, right? Half plus 1, 3 by 2. So a square plus y square raised to 3 by 2. Okay, this is the relation at the equatorial point due to a dipole. Okay, the electric field due to a dipole at equatorial point. Now again, practically this a is very small as compared to y. Okay, now mind you, y is the distance measured from the center of the dipole. Okay, so here the equatorial point, we get the field as, so we can neglect this a in comparison with y, so we'll get 4 pi epsilon naught y square raised to 3 by 2. or the square I square, and 3 by 2, this 2 will get cancelled and will get y cube. Now y cube we can basically write it as r cube, so that it is similar to the previous derivation that we obtained. So 1 upon 4 pi epsilon naught is k, this is p by r cube, okay, where r is the distance of the point p from the center of the dipole. Okay, that is very important that you remember it. Okay, distance of point p from the center of dipole. Now let us consider the directions. Okay, let us consider the directions, and you'll see that a negative sign will come over here. If you see, the dipole moment is from negative to positive, right? Dipole moment is from negative to positive, okay, of the dipole, and the electric field is along, the net electric field is e cos theta to e cos theta, which is along this direction. Okay, so you can see that those two of them, the electric field at axial point and the dipole moment, are opposite to each other. So hence we have to put a negative sign. Okay, so these two, electric field and the dipole moment, are opposite in direction, so hence the negative sign. And this is the actual vector relation for the electric field at equatorial point. And you can also note that the electric field at axial point, what was that? It was 2 kp by r cube, right? So the electric field at, so if you just had to compare the magnitude, so the electric field at equatorial point is half as that of the axial point. So it is axial point by 2. Okay, we are just comparing the magnitude. Direction wise they are opposite, right? At axial point, both the dipole moment and the electric field are in the same direction, whereas over here it is like this, right? Dipole moment is like this, electric field is like this. That is the vector relation. Over to the next derivation. Prove the Gauss law, which says that the flux through a surface is the charge enclosed by times 1 upon epsilon naught. Okay, so here we'll be just proving it for the point charges. It's not that important, but they might ask for board, so you can prove it for point charges. Okay, so here we'll have a point charge q. We'll choose a Gaussian surface, which is a sphere, okay, spherical shell basically, and we'll prove it for this. You can see that the area vector, which is along the normal, will be always perpendicular to the surface of the sphere, right? And the electric field due to plus q, now we'll place it at center, but it can be anywhere inside the sphere. So the electric field due to this will be also radially outward, right? Due to plus q is also radially outward. So you can see that the normal to the surface and the electric field will be in the same direction. Okay, that will help us later. So the flux can be written by its definition, by its very definition. It is E dot dA cos theta, integration, right? Integration E dot dA, flux through a small element, and will integrate it. E dot dA, this is small element dA, and will integrate it over the entire surface of the sphere, surface area. Okay, so electric field is uniform, so we'll take it out of R. So we'll consider this radius as R. Okay, electric field uniform, we'll take it out and we'll integrate the area. Now you can also see that before that we can see that this will be E dA and cos theta, right? E dA cos theta, E dot dA is E dA cos theta. Now theta is the angle between electric field and area vector. Now the direction of the area vector is along the normal, so you can see that electric field and your area vector are in the same direction, right? N cap and E are in the same direction, so cos of 0 is 1, right? And you can write this simply, right? So electric field due to a point charge at distance r is 1 upon 4 pi epsilon r q by 4 pi epsilon naught q by r square, and this is the electric field. And what is the integration of this entire area? It is basically the surface area of the sphere. It is 4 pi r square. So 4 pi and 4 pi will cancel, r square and r square will cancel, and you are left with q by epsilon naught. So flux is basically q by epsilon naught. This is not a very rigorous way of proving your Gauss law. There will be surely a better derivation than this, but you can prove it for point charge this way. Okay, so let's move to the next derivation now. Number 6 here, and the next few derivations we are going to find electric field due to different charge distributions. Here we have a line charge distribution, basically an infinitely long wire which is uniformly charged, okay, with positive charge, you can see. Okay, so here we'll choose a Gaussian surface. The two steps we are going to follow, it's very simple. First of all, we'll have a Gaussian surface, we'll choose it. The first step is to find Q enclosed inside that Gaussian surface. What is the charge enclosed? Okay, we'll use the charge distribution formulas which we had learned in the previous class. Okay, and we'll also equate in the second step E dot dA with the flux that we obtained from Gauss law. Basically these are two definitions of flux, right? So we'll equate them and find E from here. Okay, so those are the simple two steps that we are going to follow. So here we have a Gaussian surface. We have chosen a cylinder which happens to be apt in this problem. Okay, you'll know why, because basically this E dot dA, the angle between your area vector and the field lines over here, you can see for the curved surface will be 0. Okay, so that is how we choose it. So so that it simplifies the problem. Okay, so the charge enclosed in this case, so first thing is that we find the charge enclosed inside the cylinder. What will that be? That will be the linear charge density times the length, right? Remember in the previous class when we discussed linear charge density, we said dq is lambda times dl, right? The charge enclosed, the charge in a particular length dl will be lambda times of dl. Okay, the charge dq will be lambda times of dl. So if you have a charge q on an entire wire of length l, so you can, which is uniformly charged, you can say that q corresponds to l, then dq corresponds to dl, right? So here if you want to find dq, it will be q by l. If you want to find dq, it will be q by l times dl, right? Q by l times dl, q by l times dl. Okay, so q by l is lambda and this is dl. So this is how we had obtained it. Okay, so basically you can remember q enclosed will be lambda times density times length, or density times area, density times volume, as you will see in the next case. This is linear, so density times length. Okay, so this is our q enclosed. Next thing we have to do is E dot dA is equal to flux due to Gauss law. Okay, so E dot dA is what? E dot dA is the flux, right? Flux, definition of the flux. Okay, so you can see that area vector, the only thing that is contributing to the flux is the curved surface, right? If you see for the circular surface, the flux is just skimming the surface, whereas for the curved surface, okay, it's like this, right? Curved surface, the flux is passing through the surface. Okay, what is the definition of flux? The number of field lines passing normally through the surface, right? So for the curved surface, the field lines are passing normally, but for the circular surface, they are just skimming over the surface. Here cos of 90, right? Area vector is perpendicular to the area, remember. Okay, area vector is normal vector. Okay, and the flux is like this. So here for the circular surface, the flux is 0. For the curved surface, there is flux. So for circular surface phi is 0. So the only area that we are going to consider dA is the curved surface area. Okay, and we consider the electric field to be uniform, since it is at a symmetric distance of r from every point that you see. Okay, so electric field is uniform, E dot dA, and cos theta, if you see here, anywhere if you see here, the electric field is, so suppose this area is dA, and n cap is also perpendicular to the area, E is also perpendicular to the area. So the cos of 0 is 1, right? So you don't have to mention that, so, or you can mention that E dA cos of 0. Okay, and phi due to Gauss law. Okay, here we have E, we can remove it out, dA, and this will be Q enclosed by epsilon naught, right? I'll come back in a while. So I had a delivery coming. Anyways, so here the electric field and the area, I told you the only contributing area is the curved surface. So we'll have how is the curved surface area given? It is 2 pi r, and the length, so 2 pi r l, right? So 2 pi r curved surface and the length l. Then Q enclosed will be lambda l and by epsilon naught, right? So simplify this, L and L should get cancelled, and you get the relation as lambda upon 2 pi r epsilon naught, right? So this is the electric field due to a linear charge density due to an infinitely long wire. Okay, so let's derive the relation for sheet and a conducting plate now in the next derivation. The derivation number 7, here we'll be deriving electric field due to a plane sheet, and that will lead to the derivation of the conducting plate. Okay, the major difference between these two, many of the YouTube teachers get it wrong. Okay, so here the thin sheet is basically very flat. Okay, it's two dimensional. Here we have here you can imagine something like a cassette. Okay, and here you can imagine a plate, a paper thin something plate. Okay, a sheet basically, as the name says, and this is a plate. Okay, this is like a cassette. It's three dimensional. It has a face in front and it has the face at the back. Okay, this is a sheet, which is meaning it's just one thing. What is in front is at the back. Okay, so if the sheet is charged positively, it is positive on this side, and other side if you see, it is also the very same face. Okay, it's positive. Okay, but here you'll have two different faces, in front and backward. Okay, so here it is, if you positively charge the front face, you positively charge the back face. Okay, so these are two different cases. Okay, so basically it will change the Q enclosed, and that will change the relation just by a bit. Okay, so here first our job is to find Q enclosed. Here I've chosen the Gaussian surface as a cuboid. You can also choose a cylinder. Okay, so Q enclosed here will be basically this area, right? So basically here I have not done justice to the diagram, but here the basically your plane sheet is like this, and your Gaussian surface is somewhat I need to close this, I might spill. Okay, so Gaussian surface is somewhat like this. Okay, it's passing through it. Okay, so basically this is what you should imagine. Okay, so it actually spilled. Oh my, let it be. So here the charge enclosed will be by this, right? This face is enclosing the charge. If you see, we can find the charge enclosed by this face, since it can be imposed on this, right? The charge enclosed will be, so here it is surface charge density, right? So the charge enclosed will be surface density times the area of this face. We'll consider the area of the two faces to be A. These are the two ones that will be contributing to the flux. If you see, the flux will be outward direction. Okay, so it will be like this, like this, like this, like this, right? And this, the other faces, the other four faces are perpendicular to the direction of the electric field. The area vector here, if you see, is perpendicular to the direction of the area of the field, right? If you see, the electric field is like this, and the area vector of this face which is facing you, is like this. Okay, so they will not contribute to the flux, because cos 90 is 0, right? So only these two faces will contribute, and the area enclosed over here is Q times this sigma times A, right? The sigma is the charge density. This is a uniformly charged sheet, so here we'll have sigma, okay, the surface charge density, times the area which can be imposed over here. Okay, now E will be given as, now we have to write E dot D, right? E dot dA, that will be flux due to Gauss law. Okay, so E we can remove out because it is constant. Area, only this areas will be contributing, so I will write dA. Okay, and flux due to Gauss law is Q enclosed upon epsilon naught. Q enclosed is if you see, it is sigma A, and this is epsilon naught. Now the area, what is the area? It is also A, it is 2A, right? This area and that area, so the areas are 2A. The flux, the areas that are contributing to the flux are 2A. In the previous case, it was only the surface area. Here there are these two faces. Okay, this is Q upon epsilon naught, or you can write sigma A upon epsilon naught. A and A will get cancelled, and you will get electric field as sigma upon 2 epsilon naught. If you see, this is a constant field. Okay, so that's why you can also see parallel straight lines of this field, right? So this is a constant field. It does not depend on r. Okay, there is no r over here. So this is a constant field. Surface charge density is constant, and epsilon naught is also constant, and 2 is constant, of course. So this is a constant field, and the previous case it was inversely proportional to r, right? So you are supposed to remember these relations. Important questions are being asked. Now in case of plate, the only difference that it will make is Q enclosed, since the areas are on both the sides. Okay, the charge is on the front face, and on the back face you will have to write sigma times 2a. Okay, that will be the only difference. Okay, otherwise this will remain same. The areas contributing will be only those two areas. So those two areas and these areas will cancel now. So sigma, so I'm writing this directly, okay, upon epsilon naught. So this 2a and this 2a will cancel. We'll get sigma upon epsilon naught. Okay, so very important to remember, when it's a paper thin sheet, it's sigma upon 2 epsilon naught, and it is something like a cassette. Okay, you can imagine that. That will be sigma upon epsilon naught. Okay, so if you have two faces, it is sigma upon epsilon naught. Just one face back and forth, if you see, that will be sigma upon 2 epsilon naught. So that's about sheet. Let's move to the spherical shell now. Our derivation number 8, here we'll be deriving the electric field due to a uniformly charged spherical shell. Now all the previous discussions which were on the uniformly charged wire, the plane charge sheet, okay, and here we are discussing the spherical shell. All of these are uniformly charged. That is very important because we are using the concept of charge distributions, right? So if these were not uniformly charged, we could not obtain the relation as we are obtaining in these cases. Okay, it's very important that you remember that all of these are uniformly charged. Okay, the charge is entirely spread uniformly over the entire surface. Okay, so let's come to this problem. Here we'll consider two cases. One, when one will find the field inside the spherical shell. Now spherical shell is a hollow shell, okay, hollow spherical shell. We have distributed a plus charge Q over the entire surface uniformly. Okay, first we'll find the field inside and then outside, okay, and also on the surface. Okay, so inside, if you can see, the charges only reside on the surface of the spherical shell. So Q enclosed over here is 0, and electric field, as common sense suggests, should also be 0, because this is flux due to Gauss law, and this is 0, right? Q upon epsilon naught. So Q enclosed is 0, this is also 0, and as common sense says, flux should also be 0, and is 0. Okay, I'm not going to debunk anything. Okay, so electric field inside the spherical shell is 0. Okay, because there is no charge enclosed, where will the field lines come from? Okay, now let's come to the second case, when we'll choose our Gaussian surface outside the sphere. Okay, we are also choosing a sphere. The Gaussian surface itself is a sphere. Okay, the problem is a spherical shell, and we are choosing a Gaussian surface which is also a sphere. Okay, so that you can see that the electric field is radially outward, right, and the area vector is also radially outward. Okay, so both of them, the normal to the Gaussian surface and the electric field, are in the same direction, and this becomes cos theta is 0. Okay, so that is the way we simplify it. So Q enclosed over here will be, again, so the charge is entirely spread over your surface, Gaussian surface. So it is sigma times area. Area is the 4 pi r square, you can say. Okay, surface area of the sphere. And now let us find E dot dA. As I told you, cos is 0 in our case, and this will be phi due to Gauss law, right? Now this is Q enclosed upon, so Q enclosed is sigma 4 pi r square upon epsilon naught. Now E we can find from here, the area. Now this will be capital R square. So sorry, because this is the charge, right? Charge is spread over the entire surface of the sphere. Okay, it's not at a distance r, it is at a distance capital R, okay, on the radius of the sphere. Okay, so that is the area of the sphere. Okay, so charge on the area of the sphere. Okay, so now we have to find flux. This area is the area of the Gaussian surface. Remember that. Okay, this area is the area of your sheet. In the previous case, this was the length of the wire, right? So this is the area of the sphere, of the body, of the material. Okay, and this area stands for the area of the surface, your Gaussian surface. Okay, so here the area of the Gaussian surface is 4 pi r square. I will just write it dA for the time being, and here we have 4 pi capital R square divided by epsilon naught. Okay, here we will have E is 4 pi small r square, and here we have sigma upon epsilon naught, 4 pi r square. Okay, so this we can cancel, right, and we'll be left with E is equal to sigma r square. This might look a bit weird, epsilon r square. Okay, now sigma you can write it as, if you have to, now this is in terms of your surface charge density, it is looking a bit weird, but if we write it in form of charge, okay, we have distributed this charge over the area. Sigma can be written as, just as you can write Q is sigma into A, we can write sigma as Q into A, right? So we can write the sigma as Q divided by 4 pi r square, right? So just to show you something over here, I'm doing this. So this is Q upon this is epsilon naught, right? So Q upon 4 pi epsilon naught r square. Does this remind you of something? It is electric field due to a point charge at a distance r, right? So a spherical shell, such a big shell, a hollow sphere, a hollow conducting sphere will act just as a point charge. Okay, when you consider the case outside the sphere, if you want to find the electric field outside a spherical shell, you can treat the charge on the spherical shell as basically a point charge at point O. Isn't that interesting? Okay, so that is the case of our electric field outside the sphere. Okay, you can remember this relation and this relation. This is more useful and easy to remember. Electric field inside the sphere is 0, and electric field space. Number 9, second last derivation. Okay, so here we'll be discussing solid sphere. Okay, so the electric field due to a solid sphere. Now in the previous case we discussed a spherical shell. Okay, so there the charges were only on the surface of the sphere. It is also important to remember that this solid sphere is non-conducting. If you have a conducting sphere, the charges will only reside on the surface. Okay, and it will act like a shell. Okay, basically, so the solid conducting sphere or spherical shell will have the same relations that we have obtained previously. Okay, this case will be different since we have charge also inside the conductor. Okay, we have planted charge uniformly over the entire volume of the sphere. Okay, in case it was conducting, it will only reside on the surface. This is a property that you will learn in the next chapter. Okay, so this is a special case for non-conducting solid sphere. Okay, now we the only relation that will change is inside the sphere. Okay, outside the sphere it will still act like a positive shell, okay, or a point charge you can say. Okay, so the outside and on the surface of the your sphere, the relations are going to remain same for the spherical shell and the solid non-conducting sphere. Only the relation is going to change inside the sphere. For the shell it was 0 because there was no charge inside. Here there is charge inside. Okay, so let's find that. So Q enclosed will be nothing but we can find it using rho into 4 upon 3 pi r cube, right? Now the charge is spread over the entire volume. Now we have chosen a Gaussian surface, small r inside, you can see this. Okay, inside the sphere. Okay, we wish to find the area inside, so it is the field inside, sorry. Here Q enclosed will be given as rho times, rho is volume charge density. Now we are talking in terms of volume, right, times volume. So what is the volume inside, right? We want to find the field due to those charges inside our Gaussian surface. The outside charges will not contribute to the field. Okay, so here inside this surface we have 4 upon 3 pi r cube. Okay, now we can write the definition of our flux, and this we can equate to that we obtain from Gauss law. Okay, this will be Q enclosed upon epsilon naught, and here you can see that the electric field vector due to this positive charges is outside, and the area vector of the of the Gaussian surface, spherical Gaussian surface that you have chosen is also outside. Both are in the same direction, cos theta is 0. Okay, basically the same story again. Okay, cos 0 is 1, cos theta is 0, theta is 0. So here area of the Gaussian surface, remember this is the area of the Gaussian surface, this will always be area. Okay, this might change. Okay, this might change on the nature. For the line charge it was L, for the surface charge it was area, and for the volume charge it is volume. Okay, so this might change depending on the type, but this is the definition of flux, right? So this is always area of your Gaussian surface. So area of our Gaussian surface is 4 pi r square. Q enclosed is rho and 4 upon 3 pi r cube upon, I think, 3 upon epsilon. Okay, so 4 pi can get cancelled, and what do we obtain? We obtain a relation saying E r square will also get cancelled with this, so we get a relation which says rho r upon 3 epsilon naught, rho r upon 3 epsilon naught. Now this is the electric field inside a solid non-conducting sphere. Now to make it interesting or more memorable, you can substitute this rho will be just like you can write a Q enclosed as rho times this, you can write rho as the entire charge. Now rho, we are writing it for the entire sphere, entire charge divided by the volume, 4 upon 3 pi r cube. This charge is distributed over the entire volume r cube. Okay, so rho can be written as Q upon 3 over here, 4 upon 3 pi r cube, and here we have r and epsilon naught. I hope I didn't miss anything. Okay, so this is Q 4 pi epsilon naught r by r cube. Let me check the relation. Is it the same? Yes, it is the same. Okay, so this is the electric field due to a solid non-conducting sphere inside the sphere, and outside it is all the same as your spherical shell. Okay, so it is kq by, you can say kq by r square, just like a point charge. Or on the surface, I think last time the camera didn't catch it, so catch it this time. So this is kq by r square. Basically this is r equal to r, right? So these two are continuous, so basically the value you can just obtain this at the surface, electric field at the surface, by substituting r is equal to r. Okay, r is equal to capital R at the surface, right? So at the surface and outside it remains the same. Only difference is that electric field inside the spherical shell 0, inside your non-conducting sphere it is something. Okay, it is actually dependent on r, directly proportional to r. This all is constant. If you see, this is radius, this is constant, this charge on the sphere, this is total charge, remember. Okay, this total charge on the sphere is also constant. Okay, but it varies according to r. So E is proportional to r inside a solid non-conducting sphere, and it's inversely proportional to r square in other cases. Okay, and this is constant. This whole values are constant. I will write small q. Okay, and this is 1 by proportional to 1 by r square. This is constant. Okay, we had seen the nature of this class, of this graph in the last class. You may watch it after this video. Okay, so let's go to our last derivation for the day and let's wrap it up. Derivation number 10, the final derivation for the day, will be deriving the torque on a dipole placed in a uniform electric field. Okay, so uniform electric field, how is it denoted? It is denoted by equispaced parallel lines, right? So this is uniform electric field, as we can see. So we have a dipole which is placed in this field, plus q minus q. O is the center of the dipole. You can see that the force on the dipole, net force, is, if you see, the force on this particle is QE, right? And the force on this particle is minus QE. Let's write that magnitude wise, it is 0. Okay, so net force plus QE minus QE, net force on the dipole is 0. Okay, so this is something that you might want to remember, that the net force on a dipole placed in a uniform electric field is 0. Okay. Now let us find the torque, since that is our objective. So you can see that these two forces are acting along two different lines of action. Okay. So if you see this force is like this force is like this. Okay, they are not along the same line. If they were along the same line, they would not produce any torque. Now they are along different lines, so it is rotating, right? It is this is pulling, the electric field is pulling over here and pushing over here, so it is rotating the dipole. You can see that. Okay, so that will give rise to torque of the dipole. Okay, that will give rise to torque. Okay, so we can find the torque on the first one, that will be r cross f, right? So I can write ob, or this is basically, this distance is a, it's also a, use it later, ob cross r cross f, right? So q e. Okay, we need not consider the sign when we consider the directions. Here we'll see what happens to the torques, the two torques. You can see that it is r cross f. Okay, so you'll move from r cross f, right? R cross f. So r is along this direction, f is along this. So r cross f, when you move from r cross f, it is pointing towards you. And here if you see, here we have r again and cross f, so it is r cross f again towards you. Okay, so we have to add the two torques. Okay, so both the torques are towards you, so we'll just have to add the two torques. Okay, so torque 2 is ob oa cross qe, force, right? Now add these two torques, because the net torque is just the sum, we just now saw it, torque 1 plus torque 2. Okay, so we'll get qe common, so we can write oa plus ob. Okay, and we have cross qe. Now q is a scalar, of course, charge is a scalar, although it is positive and negative, but it is a scalar. oa plus ob is nothing but 2a, right? 2a, and this is q, and this is e. Now this is cross product, so this has to be a vector. And can you identify that vector? It is, I can take the q over here. Okay, now you can identify that vector. This itself is a vector quantity, so that quantity is nothing but your dipole moment, right? Q into 2a, charge into distance of separation, is dipole moment. Okay, and the relation that you obtain for torque is P cross E. Okay, or you can write it as P E sin theta, magnitude of P, magnitude of E into sin theta. Okay, and the maximum torque will be PE when sin theta is 90, sin 90 is 1, so maximum torque is PE. So when it is in the 90-degree position, when it's like this, perpendicular to the field, okay, the torque will be maximum, it will rotate. And when the torque will be minimum, when theta is 0. Okay, if you have the dipole along the field, in this case the two forces will act along the same direction, plus QE minus QE, they will cancel, torque is 0. Okay, so this is the relation between torque and your dipole moment, or this is the torque that a dipole will experience in an electric field, in a uniform electric field. Okay, so that was all about today's lecture. I hope you really enjoyed it. If you made it this far, do consider subscribing. If you wish to follow this series. We are covering one shot chapters, okay, all the concepts in one shot, and the second series is all the derivations in one shot. Okay, if this is something you want to learn, if you want to speed up your learning, you might as well consider subscribing. Okay, so I'll see you soon in the next class. Till then, keep enjoying physics.